So our to-do experiment is measurement of power factor meter, and this is the objectives of the experiment. Learn the structure of the power factor meter, learn to direct measure the power factor meter, learn to indirect measure of power factor meter. So that's the objective. So we are going to look at the structure of the power factor meter, and we are going to learn what the direct and indirect method of measuring of power factor meter. Okay. And this is experimental equipment. We have EMTS-01 control panel, EMTS-04 analog meter 1, EMTS-07 analog meter 3, EMTS-10 for laser lamp, and you have a connection wires. Now let's see the experimental principle. Let's see the experimental principles. The power factor refers to the cosine of phase angle difference between the voltage and the current in AC circuit, and its symbol is cos theta. The power factor is the ratio of active, that's the real or true power, to the apparent power in value. So that is the cos theta is equal to P over X, which is equal to the P over root P square plus Q square, P being the active power and the Q being the reactive power. Many electrical devices operate based on the principle of electromagnetic induction, transferring and converting energy by the establishment of an alternating magnetic field. The reactive power refers to the power needed to establish alternating magnetic field and magnetic flux. The reactive power is not useful power, but it does not convert into mechanical energy or thermal energy. So both reactive power and active power are indispensable in the power supply and consumption system. In the operation of power grid, the power factor represents the degree of utilization of the apparent power flowing out of the power supply. The power factor should be as large as possible so that the reactive power can be lowered to the minimum and the apparent power can be largely converted into active power, and thereby enhancing the electrical energy transmission rate. So now let's see the two methods. So we have an indirect method. Indirect method, the power factor of a single phase circuit can be calculated through the following equation. That is the cos theta equals to the power over voltage times current. So 3 meters can be used in the experiment, namely the power meter, the voltmeter, and the current, the ammeter. The power factor can be calculated after power, voltage, and current are gauged by respective meters. In regards to the symmetrical three-phase circuit, the power factor, that cos theta is equal to P over root 3 VIN I. So the power factor can be indirectly measured by the use of three-phase total power, the line voltage U, and the line current I. So these are the indirect method. Indirect method is a calculation. So you get your power, voltage, and current. Then you use the cos theta is equal to P over VIN I. Then you get your power factor. Now let's see the direct method. So direct method was like electrodynamic power factor meter. Adopts the structure of ratio meters as shown in figure 2:1. So this is the figure 2:1. So this is the structure of the power factor meter here. In the figure, it represents two sets of fixed coils connected in series with identical parameters. So you talk about that this is the A, this is the fixed coil is connected in what? In series. So this is the coil 1, coil 2 is the fixed coil that is there with identical parameters. B1 and B2. So these are B1 and B2 moving coils with identical parameters. So they are the moving coils. B1 and B2 are there. This is a B1 and B2 are the moving coils, which are crossed into fixed coils connected in series with identical parameters and are close to form an angle on the revolving shaft. So the fixed coil A establishes its magnetic field, and the two moving coils B1 and B2 generate deflection torque in the field. When the two are balanced, the moving part is established and the needle points to an equilibrium position. The deflection of angles is decided by the property of the load, that is the polarity of the angle. Under the conditions that theta is equal to 0 or cos theta is equal to 1, the needle deflection towards one direction when an inductive load is connected, and the needle deflection towards the other direction when a capacitive load is connected. So this is the structure. This is the structure of what? Of the power factor meter, how it works. And this is how I've shown it over here. Experimental procedure. So this is we have a circuit diagram here. That's what we're going to follow to perform our experiment. And when we look at here, this is the wiring diagram of the experiment. So we have the ammeter here, power watt ammeter here, power meter here, voltmeter here, our adjustable resistor here, and the fluorescent lamp here as well. So when we look at the live wire here is so anywhere you see the ammeter, that's the live wire. So always live wire is passing through the ammeter, and also you see ammeter is what is in series what in this wiring diagram, while the voltmeter is always what in parallel, the wiring diagram. So from the live wire passing to the ammeter, from the output of ammeter, let's go to the wattmeter. So when you look at here, wattmeter is what consists of what? Voltage and current. So that's why we see this bridge sign over here. From you to this side, we jump to this side. That's why. And the same connection of wattmeter is the same as well the connection of power factor meter. So from the output of wattmeter, it goes to the power factor meter. So now, after the power factor meter, it goes to the voltmeter, and you tap from the voltmeter to the fluorescent lamp, and we see the neutral. So the neutral connection, the wire is passing through the adjustable resistor. Then from adjustable resistor, adjustable resistor is in series in the circuit. So from the output there, it goes to the wattmeter. Then you tap from there to the power factor meter. Then you tap from power factor meter to the voltmeter. So from the voltmeter, you tap it to the fluorescent lamp. So this is the wiring diagram of the experiment. So now let's go and perform the experiment itself, and let's see how it's going to behave. start from the live wiring. So this is our voltage sources. So we'll pick one phase because it's a single phase. That's why, so we are picking the red phase. Now, from the red phase, according to the wiring diagram, from the voltage source, we go to the ammeter. So this is my ammeter. This is the ammeter. Now the ammeter is what? It's in series. So live input and live output. So we take it from here. That's the live input. So the ammeter doesn't work. Ammeter is only what live wire, that is what's passing through. But when you come to the voltmeter, it's in parallel. In parallel with the circuit. So we have a live and neutral. While the ammeter is in series, so only live that is passing through the ammeter. Okay, so for an output of the ammeter, then it goes to what? To the power meter. So this is the power meter here. Then we know the power meter is current, voltage and current. It's a multiplication of voltage and current. That gets what? The power. So we have the voltage here and the current here, current side here. So we first from the ammeter side go to the voltage side of the power meter. Then what we multiply it. So we start from here to the current side. Now, after you get to the current side, now the current side, current is always what? In series. So now here serves as well the output of the current side serves as well the output of the power meter. So we'll take it from there. Output of the power meter, we'll take it from there. Then we send it to the power factor meter, which is the voltage side of the power meter. Let's take note. The power meter and power factor meter, the connections are the same. So the same connection we did, the same thing that we are going to repeat it here. So the output from the current side of the power meter goes to what? The voltage side of the power factor meter. So the same, we are going to repeat the same thing over here. The same thing. So now, as this one, the output of the meter here, the power factor goes to what? To the voltmeter. So this is our voltmeter here. We have the voltmeter here. So this is our voltmeter. Go to the voltmeter. Then we drain from the voltmeter. So from the voltmeter we tap it from there to the load. So this is our load. We have it here. Okay, so now after we have connected to the load, now we are done with the live wiring. So let's go to the neutral wiring. We pick the black cable. We pick it from, so this is our neutral sources. So the neutral is passing through there. It's passing through, so it's passing through the resistor because the resistor is what? It's in series in the wiring diagram. So it's passing through. Pick from here. So put from here, so input and output from this side. Then from there go to the power meter. Then we will tap it from the power meter to the power factor meter. The same thing will lead you to the voltage meter or voltmeter. We'll break it from the voltmeter to the fluorescent lamp with our load. So now we are done with the wiring. So now what we are going to do, so let's take note here. Here, when we look at the fluorescent lamp, there is a dot line over here. There's a dot line so this is a starting relay. So there's a dot line there at the starting relay. So we need to push all the dot lines. So we have the dot lines here. We need to push all the dot lines. So this is the dot lines we are seeing over here. So we need to close all the dot lines. So this one we are using what? We have a 20 watt and 40 watt. So if you want to take 20 watt, we'll pick it from here, then we take it from here. If you want to take the 40 watt, we'll pick it from here to here. So you close the dot lines. So we select what? 1 wattage. So so let's assume we are taking 40 watt. So if it's a 40 watt there, then we need to close this one. Then we close this one. So we select the 40 watt. And the starting relay, we close this one. Then we close this one so that we got able to start the fluorescent lamp. Okay, so let's close the dotted line. So I'm using this one to close the dotted line. I'll put this, and I'll close this. So now I'm done. So first I need to check the continuity. So I'll take my multimeter. Then I'll on it and tune it to the continuity symbol. So for now I'm going to check the continuity of the. So I want to check the continuity of the red one. So I will place one at the red one, then I will use the other one to test it. If the red will have a connection with the black one, with the light have a connection with the neutral. So that's what I'm doing. Check the continuity. So only the red wire cable that's going to be, but when you check the black, it won't be. So if it doesn't be, then it means that the light and neutral doesn't have any connection with each other. So the red is going to be optional. So I'm done. So since we have not energized it, our meters are what? At 0 point. But when we look at the power factor meter is at what? At 1. Also we start from what? 1, which is 100% downwards. Okay. I'm going to energize it. So I'm going to bring the system on. So turn the circuit breaker on. Then the key is on the key. Okay, so now let's see. So now I've not applied the load. So we see, if you see, look at the ammeter is at 0, while the power factor meter also at 1. So by the voltmeter is just reading the incoming voltage as what is there. So the power is remaining, but the load is what? It's not on, it's off. So the power remaining, power factor remaining 1, and the current remaining 0. So as we are applying it, you see that it will start reading it. The voltage is reading the incoming voltage. So the power factor is at 1, while the power meter is within 0, because there is no load as at now. So when I apply the load, all the meter will start reading. So now I'm going to introduce the load. Okay, so now the load is there. So now you see all the meter are starting reading. This meter are starting reading. This meter are starting reading. The current is reading. That's 0.2, while the power factor meter has dropped to 0.99, and the voltmeter is also reading 140. So you see, that is leading here over here. Okay, so this is what you see over here. It's clear here. That has moved toward to the lead side. Okay, so this was the breaker. So as we use the inductive load, our power factor what? It will be lead. But if we are using a capacitive load, our power factor is going to what? To be lag. It's moved to the lag the other side. Okay. So let's increase the resistance. So as we increase the resistance, you see. As I increase the resistance, the voltage also goes down, while the current also decreases. So both the current, as you increase the resistance, both the voltage and the current will decreases. While the power factor is what? Is moving to what? To the 1. It's moving up, it's increasing. So let's say as you increase the resistance, so the power factor also is trying to what? Increase it. Okay, so now let's use the indirect method. So to get the indirect method, we have the voltage and the current. So, and this serves as what? The apparent power. Then we have the power. That's the active power also here. So now what we are going to do is that to get the indirect method, we say the cos theta is equal to the active power divided by apparent power, which is the voltage times current. So that's the indirect method. So indirect method is involved with a calculation. So we use what? It's the cos theta equals to the active power divided by the voltage times current. So that you get what? That's your power factor. By the direct method, we are using what? Electrodynamic meter. So this is the electrodynamic meter here. So it's going to give you what? Straightforward what? The power factor. So this is the power factor. So we can see this one. But this the indirect method, you need what? Calculation. You need to calculate it. Using this readings and this video to get your calculation. Okay. Through this experiment, we have learned the structure of power factor meter and the methods of measuring the power factor meter. That's the indirect method and direct method. Furthermore, we can understand the physical significance of power factor and the means of enhancing it. We have also learned the analysis that the pros and the cons of using direct and indirect measuring method. So this is the summary of the experiment of what we have done so far.